to the stream if you're watching this in the future. I'll be doing a somewhat short stream. Since I've been streaming most of the day. Let's see. Do I need to update my YouTube chat here? I probably do. Let's see. Probably. Let's see. It hasn't invalidated this chat yet for some reason. But let's see. Cost ducks here. It's definitely another chat, so let me just change the thing here on the stream. Not interact. I need to change it. Okay. And let's interact with it. Set it to live. All right. Is that it? Yeah, I think so. I could do the same for the Twitch chat. Maybe I'll do that in the future. But I do like a simultaneous chat log, or what we would like to call it. Anyway. Yeah. So. I wanted to do a bit more work on the level editor, and I'm gonna do a bit of object picking work, but I would like to be able to set our application here at a current state. So we'll create a enum here, enum class, which will be application state, which will be default. Let's do editor. As our states. We will store our application state. Let's see these app state, which will be initialized as the default state. In our application, during our update step, let me just swap some things around. Okay. Inside here, we will allow for camera controls. Let's see, let's do something like this. Camera controls. Let's see, do we have, was key pressed? We have F7 implemented. And what does our table up here? Yeah, 21 is F12. So let's see if we paste that, whoops, if we paste that, WK F12, we will do 21 here. And then we do F11 as well. Because I wanted to bind these keys to changing our application state. Let's application controls. Let's scope that. Keyboard controls. And then if the input system was key pressed, virtual key F11 pressed F11 key, and of course we will do the same thing for the F12. App state will be application state default, and this will be editor. Print in swapped set to default mode, and print set to editor mode. There we go. Temporary input polling, temporary input polling for testing, default state. So if equals application default, we check for this, otherwise we don't. Let's see, we don't do this anymore. Store debug information here regarding points needed to be rendered. Maybe we should actually just move this. Let's remove that. Buffers for debug information. Buffers, plural, please. Okay. physics loop. Well, if the app state equals application state default, we will do this. Particles, rigid body objects. Okay. Let's collapse all this. Some player controller stuff. Dynamic object creation. I don't think we need that anymore. I mean, do we append anything? No, we don't. We do the submission afterwards, so let's just move this into the graveyard because I don't think we need it. And anyway, it will just be in the graveyard. Man, I've dumped a lot of stuff in that graveyard. Code graveyard. Okay, we have the player controller, camera controller. I don't think it should be called on update. It should be called update. So we will change that. It doesn't really make sense on update. We will just update it. This is some old UI stuff. We don't need that anymore. That's the temporary design document. Okay, let's see. The debug lines, let's just group them together since we will use this during our current work session. Okay, let's move this. Let's see, AABBs, lines. Let's do something like this. Points. OBBs. And the onCreate function is somewhat cleaned up. We don't need this. Let's do this. Spheres. let's see, let's put it up here. Everything is more tidy now. Physics loop. And let's see if we're in debug mode. Let's see. Debug mode is right there. We could create a static flag that is equal for all applications. Yeah. Let's see if we do something like this, static, debug mode. And when we instantiate our application here, we will do bool application debug mdebug mode equals false. And whenever we create a static function here, let's just do it temporary static function to enter debug mode. Static void inline, already static inline void toggle debug mdebug mode equals the opposite of debug mode. There we go. And this should be fine. Everything should still compile, right? Yeah. Great stuff. So we have our uh, render, debug, visuals, if set uh, render UI system. I'm pretty sure this could be updated up here and everything would be fine. Let's scope this. Do the update render data and submit transient objects. Let's scope that. And then we have our design document. Design doc. Let's see. Much wow. Let's see. Great stuff. Everything seems to be working. Okay, so that's cleanup of the main method here. For some reason, this doesn't get recognized as a scope. I don't know why. Let's hide that. Let's create a scope here. Okay. So we have our setup here. This is not a scope for some reason, but our update step here is way, way, way more pretty. Oh, wait a minute. Okay. I need to set the pass data here. Outside of the scope. Hello, man. There we go. All right. Let's close some of these files here. We don't need all of them. How are you doing, buddy? I'm pretty good. How about you? Okay, inside our level system here, we will include our application just to be able to call the static function. Let's see, we're inside our update function here. I'll close the load and init functions here. Let's do a button here, if UI system to button mp editor context with a title called toggle debug info application toggle debug. There we go. So now we should be able to toggle our debug information here. Yeah, we are. We can do our whoops. Well, is it all bound to, well, the F keys are probably bound, aren't they? Let's see. Oh, I only check for them, but I don't store them. That's why. That's why. So we need to process them in the same way that we do the other keys here, 21, and then for this one, 20. Okay. So this should allow us to toggle, wait a minute, the Visual Studio here overlaps. Let's see if I run the application. run the application here and press F12. I should be in editor mode, which means that this is not moving anymore. And then if I set back to default mode, it starts moving again, and I can use that. And inside editor mode, I can't use any of these controls, but inside default mode, I can use that control. Okay. So it's Visual Studio that overlaps. Let's see, debugging, F12. Maybe we want F8, maybe F9 and F10. Let's just implement F8 here. 17 and implement F9 and 10. Because I will have to test whether was key pressed. Okay. So we do 17, whoops, VK F8, F9, 18, and then F10. Okay, let's hope these buttons don't overlap. Let's see, F9, VK F9, and VK F10. F9, F10, F9, F10. Okay, we can do that. But F11 and 12 uses the debugger. So whenever we are in Visual Studio mode, we can't control, or rather, we can't use those buttons. Anyway, our level system editor here will actually use the same way of polling here. We will include our input system. This will be duplicate values. We could also make that static, actually. We could also make that static since we already, I mean, the application state will be static here. Static flags for program wide use. Let's see in our application here. Equals application state default here. Static inline application state. Get app state. Return the app state here. So let's see. Are we allowed to change this? I'm not sure. Whoops, that's the wrong button. I mean, now I have disabled these buttons here. Let's see, and we are back. Okay, so it doesn't care that we change the static variable since it's the same for each instance of this class here, so that's great. We can now get our app state in different areas of this application. So if application get app state equals application state editor, we do some stuff. Let's see what happens if we move all of this in here and allow us to toggle the editor. Whoops, I keep on forgetting that those buttons are bound. Yeah, so we can swap to and from editor mode. Great stuff. We should, of course, add some widgets over here inside the application that are running permanently. So if we swap this on and off, yeah, the debug visuals doesn't get rendered whenever we are in editor mode because the physics is disabled. As you can see here, we can freeze it in time. Funny stuff. And we can toggle the debug mode off. Whoops, I need to release my mouse here. Great stuff. Okay. I would also like to change that the coordinate system here is not supposed to render, so to do, let's create this up here because we need to see render to do. Move the coordinate system into the debug info buffers. Since we want to be able to toggle it. Okay. With the default / play mode versus editor mode. Nah, we just want to be able to toggle it on off with the rest of the debug info. Yeah. Let's see. Yeah. I try to make a habit of putting the debug info, or rather the to-do lists inside the headers. Yeah, I do the same thing here. Yeah. So I don't get confused. Oh, this should be Hello, buddy. This should be our in our header. I don't know. Maybe yeah. Um, maybe the system went to sleep mode. I was away for a pretty long time, but you came just in time since you wanted to see the object picking calculations. So mm, so there's an argument for well, we don't need to do anything more to the input system here. So right now we have our camera information outside of the level editor. Which could be a problem. We could pass on a pointer, which is a temporary fix to our camera controller. So no matter what camera we're actually using, we will always know which camera to use for our computation in terms of picking. That means that we can actually use the uh, player camera here as a way of clicking, or we could use the free floating camera here as a way of picking. Whoops. Yeah, I definitely need to flush. Let's see. Let's do that. No need for crashing. There we go. Yeah, this should work fine. Okay. Yeah. Now we actually wait for the flush to happen. Okay. So, yeah, we will allow our level system to store a pointer to a camera controller, even though it's janky. Let's see, camera controller pointer, app. No, let's just do camera controller, which will be a null pointer. If we don't set it, we will store a camera controller here. Janky will be handled when camera controllers are moved to the level container. I think cameras probably should be part of a scene slash level. At least we will make it so. So in our initialization step here, oh, I keep on forgetting that is some application specific initialization. We will initialize. Oh, they're actually kind of dependent on each other. Okay. Well, and we will do it another way. Well, we don't want to make it static, I think. We could make our application singleton. Okay. For now, we will create a singleton application. Let's see. Let's do some static application here. Instance. Let's do that. Yeah, this should work fine. Yeah. Okay. Did I not initialize it? What is the problem here? Flush. Yeah, there's some problem here. Okay. I'll fix that. Eventually, do we regularly get crashes here? No. I should also check out the debugging stuff here. Well, we haven't gotten any errors. Anyway, okay, I'll fix the cleanup of the application off stream. It's been a while and we probably need to do some housekeeping in terms of releasing everything properly. Anyway. Git app, and we return an instance here. Okay, so now instead of passing along a camera controller pointer and doing stupid shit like that, we instead create a function. Although it's not static, it will return a camera controller reference. Get camera controller. It will return m instance camera controller. Or it could. And let's just get camera controller. M camera controller. Okay. So we don't need that. Inside our application, we can simply call application, or rather inside our level container here, we can call get app. Yeah, I did. My mistake. All right. So we can access our camera controller here and get our camera data. Okay. So if we're in editor mode and we get a um, um, let's see, mouse clicked. Let's say we click our left button here. We want to calculate. Oh, maybe we have a function actually that will return the. Let's see, the mouse position as well. Get click position. It was down and it changed. Yeah, get click position is probably better since or we could just ask for the mouse position when we do it, since we only want to do the calculations anyway. Input mouse position equals input system. Let's just use the namespace input here. Let's do the input system. Get mouse position. Mouse position. Mpos equals that function. So we grab our hello. So if we're in editor mode, we get a mouse click. We could do a struct here, application size, which will hold a unsigned int width, unsigned int height, which we will initialize as 0. And then we can application size. We can get app size. And let's return the return an application size with the values m width and m height. Okay, since we need our screen size to be able to translate into the screen space coordinates. Let's see, screen space coordinates of DirectX. Screen space DirectX12. Let's see, coordinates. Are there any nice? Yeah, so this is actually uh, let's see, clip space. Or no, it's maybe normalized device coordinates DirectX. Let's see, isn't that it? I can't remember the name. Yeah. Oh, that's for OpenGL. Anyway, it's the DirectX equivalent. The one that I think, is it the same? Well, it's probably the same anyway. Yeah, I think it's the same. Although the X and Y. Yeah, it seems like everyone does this. So we're trying to translate backwards from. So the translation goes screen space coordinates xy in terms of pixels. Then we need to traverse down from screen space coordinates into normalized um, device coordinates x and y in terms of absolute values between -1 and 1. So for instance, in our UI system here, let's see, in our renderer, UI, render UI, right here, you can see the x spans from -1 to 1 and the y from 1 to -1. It's actually not screen space, it's normalized device coordinates. At least for DirectX. As far as I remember, at least that works. I know that that works. And I'm pretty sure every thing that gets translated by the view projection matrix ends up being in that coordinate system. Anyway, I think I'm using the correct terms. X, Y. Uh, yeah. DirectX coordinate systems. Screen. Does this That's the UV mapping. Uh, uh, let's see. So -1 to 1. Yeah, Vulkan uses the same. Blah blah blah. Yeah. Okay. Yeah. So it is. Anyway. Anyway, I'm not gonna bother figuring out which API uses what kind of coordinate system. It's still normalized device coordinates for x and 1 to -1. Oh, is it the opposite actually? No, that's right. For y. So we need to translate from this into this, and then from um, that into world space, where we will do our testing. Okay. Now into this is view space because we use the projection matrix, as far as I remember, to translate from that. And then into world space. So we need to transform this x and y of the mouse position into something that we can use. Since we from the view space use the projection matrix to translate into normalized device coordinates, and by using normalized device coordinates in our pixel shader we get screen space coordinates. We need to kind of like use the projection matrix to get a idea of, let's see, um, anyway, what was I saying? We need to do some conversions. We need to use the view projection matrix. I won't be doing the math itself since it's uh, um, somewhat cumbersome. Projection matrix for our application. Get app, get camera controller, get let's see, what do we have of functionality in here? We can view mat, projection mat. Okay, so let's just get the camera. Get the camera, get view mat, or rather projection matrix. And then we will calculate a vector in view space using this matrix. So our vector will stem from the origin, which is the position of the camera. So that means that the g vector origin is equal to simply this, because we're in view space right now. We can add that into in case we want to translate or whatever vector we calculate. Also, let's do a g vector. We want to cast a ray from the origin, ray direction here, where we need to specify an x and a y, and this will be 1 and this will be 1. Since we're in view space and we're creating a ray that, for instance, if you imagine this entire screen here is our camera, when I click up here, I'm supposed to cast a ray in that direction. The direction is perpendicular to the x and y coordinate axis, so that means it goes directly into the screen. So this, let's see, float x and float y is actually the direction of the vector. So it starts at our camera position here, and then it traverses somewhere out depending on where we click. So if we click straight in the middle, the ray will go straight forward. If not, it will have an angled direction a bit. Yeah, and we will translate that. Hello, man. I'm creating a game from scratch. So right now we're doing object picking so that we can do a simple click inside our editor here. Whenever we're in editor mode, I want to be able to click an object and then select it so I can edit it. So that's the basic idea. Okay, in order to calculate the x and y coordinates for this vector here, we need to use a formula that is separated into two. Let's see, let's just write a 1 here for now. Actually, this you won't know this unless you know the formula, but this will actually be our diagonal value. And since it's stored in a register like that, I'll just do like that. We will multiply by our mouse position here. Mouse pos, let's see, dot x. We will double it, and we will divide by our application. Let's see, let's also store an application size struct here, screen size, which will be our application .getapp .getapp size, and we will have our screen size here, width, and if we double the x and y coordinates and translate them into our or rather divide by our width, we will get something that ranges from 0 to 2, since we double the potential screen position, meaning that if we're at the maximum x coordinate out here, we will have our exact screen width, and we will double that, and then we will divide by our screen width, meaning that yeah, we will have something that is clamped to 2, but we will subtract 1 since our x coordinates needs to be clamped between 1 and -1 and 0. We will do somewhat the same thing here for the y coordinate. Let's do the y position here, and then screen size dot height. But here we will need to add 2 because right now we take double negative of our y and divide that by screen height. Let me see. And then is this actually correct? Let's see. I think so. Maybe I used a wrong one. Yeah, you could do it in a different way. Anyway, we will take the other part of our our projection matrix here and divide by that, and we will have a ray here. What up, Penguin? How are you doing? And we will use a register function here to dump our ray direction. Let's see. Whoops, I won't be using that. I will be doing that. We need to be in editor mode. Okay. Read access violation. Huh. Let's debug this. So we're fine. Hi, welcome. Have we simply not initialized any camera? Let's see, not init, in on create camera controller. Cameras. Let's see, maybe I need to set current camera index should be 0. So this should be set. Let's see, this autos, this. Get camera controller. Let's see. Is it a problem with this function? Let's try changing it to a pointer here. Yeah, somehow our subscript here is out of range, but I don't know. Mm, current cam index. Our application should get camera. Maybe we just want to. Okay. Let's try hard coding this into the function here. It still doesn't want to do that. Okay. Let's see. Oh, I know why now. I know why. It's because this is not set. We of course need to return this instead because it's on the static one. Yeah, so it's not valid. Let's change this back. This should be fine, right? Let's see. Nope, not yet. Let's see. Let's get a static camera controller here. What if we simply circumvent that and then do like this? Let's see. Let's just try doing this temporarily. Let's disable all of this. Yeah, so even that one fails. Let's see, does this one fail? Nope. Let's do what we did before. Git app. Let's create a camera controller reference ref. Whoops. We then need another call in order to be able to stop the breakpoint. Okay. Window handle. Okay, it's empty, the reference here. For some reason it's empty because it's probably not static, so okay, yeah. Let's see. Maybe if we do okay. It's related to the static stuff here. Okay. Since I really don't like this singleton stuff anyway, I mean, the application should be in the same state no matter how many instances we create. So let's simply do something else here. I mean, these are global states, and they will be created on all applications. So we will either be in debug mode or default mode. That's why we do static. Welcome. I'm creating a level editor for my game here. So right now I'm doing a bit of coupling. Let's see, application pointer app. I'll show you in a minute what I mean. Application. I just need to set this up. Whoops. This. Okay, and let's just quickly set up MP application get, oh, did I remove that function? Application size. There we go. And camera controller. Okay, get app size. We will set this to what we did before. Application, not MP app. Get camera controller, get camera, get projection matrix. And then we can do our calculations here. I think this should work. There's a bug somewhere. Unknown identifier. Did I update in here? I did. MP app equals app. Application, we should have a, I mean, I included inside the level system here. Well, no. What is up with that? Did I miss something inside this header file here? I might have. Did I? Huh. No, that's weird. Let's see. Warning. Error. Oh, wait a minute. Is it this? No. Level system. Huh. It doesn't like what I've done. Uh, uh, yeah, I changed some stuff here, and it was running just a few moments ago. So let me revert back here. Maybe I just do a pre declaration here. Pointer app. and then include the application header here. Maybe. There we go. So yeah, I was including the thing that is including, and yeah, it turned out to be a miss. Okay, let's enable edit mode, and let's see. Now we cast our array here. You might be able to see it. Let me just move this. So when I click the center of the screen, the array that we're supposed to cast in view space coordinates are like that. All right, great stuff. So now we cast array in view space, but we need to translate it into world space so that we can actually do anything with it. So in order to do that, we need to find the inverse view matrix. So we can translate our vector here by that. So we need to figure out inverse matrix calculation. So we need to divide the adjoint of a matrix by the determinant of a matrix. Uh, 4 by 4. A lot of different calculators are available. How to, let's see. Okay, it's a video. Okay. Let me just do it. I'm pretty sure I can't find a good explanation that I can show you guys if you're watching. So we should probably just do it. Yeah. Let's see. Let's see. Let's see. Okay. I can't remember how to do it, so I'll just look at some old notes here. It's really, really seldom that I implement stuff like that, so let's see. So you saw that we need to calculate the inverse by calculating the determinant. So the idea is that only square matrices can have invertices. That means that they have to have this same amount of rows and columns. Sometimes we can't invert a matrix that is dependent on the so-called determinant, a matrix multiplied by its inverse. Yeah, exactly. Um, so let's see, if we calculate determinant of a 4x4 matrix, whoops. So we can use the cofactor expansion here. This will probably take a while. Let's see. The determinant is cofactor, so it's let's see, can we find a well, that's fair enough. Since I'm doing a game, I have to do a lot of software. All right, determinant of a matrix. Let's see here. Let's see. So the determinant of a matrix is equal to the sum of the products of the elements of any one row or column and their cofactors. Let's do it by column here, since our Matrix is what do you call it? Column major. Okay, let's see. Let's do the inline function here. Absolute mask, blah blah blah. Lots of different stuff. Where are the matrices? Multiply, multiply, skew, quaternion stuff. Okay. This is quaternion stuff. This is vector times matrix stuff. This is a 3x3 inverse. We're close. Okay. We will do a 4x4 inverse. Inline, G matrix, vector call. Matrix 4 times 4 inverse. And we G constant matrix reference here, matrix. And we create a G matrix result and return that eventually. Result. Let's for now do identity. Okay. Get identity matrix. Yeah, we will do that just temporarily. Anyway, we will calculate the determinant. We will take the let's see. Okay. Equal to the sum of the products of the elements of any one row. And their cofactors. So for a as you can see here, this corresponds to this. Oh, now I get it. Okay. So So 1, 1 will be equal to 1 times yeah, 2D arrays can be considered matrices. Excuse me for 1 second, I have a phone call. All right, I'm back. So, yeah. Um, so for instance here, I use the first column. And as you can see, yeah. Let me see. Just a sec. Since I'm feeling like I spent too much time on this, I'll skip a bit ahead. We can simply look into the DirectX Math implementation if we want to. Since I don't want to spend a lot of time doing this on stream. It's fairly cumbersome. I don't know why you would say that I'm 9 to 5 office worker. I'm pretty sure you need matrices in direct, or rather 3D computations and physics. So there's no point in just using arrays. I don't know what that even means. Yeah, buddy. Oh, that sounds exciting. Are you? Do you feel ready? Let's see. Plane operations, matrix, inverse. determinant. Well, that didn't help me at all, this function lookup. Well, that's great. Rather feel better to feel a bit prepared than not. Okay, I guess I have to do this the hard way. Mm. So oh, that sounds really exciting. Okay. I use this math so seldomly, so mm. uh, hmm. Okay. Easiest way to calculate that. Gaussian. Uh, it's so cumbersome. Okay. I'm glad to be able to help, but yeah, I do have some friends. Feel free to hang out all you want. You are very much welcome. I'm pretty sure you will find some friends eventually, if you want to at least. Uh, okay, here we have a formula. This is our formula. No, 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 no. No, you're not disturbing me. I was just looking for a way to do this determinant function here. I'm not really a great math student here. Okay. Or rather, I have never actually had any linear algebra lessons. So let's see. The first column here will be multiplied by different stuff. Okay. We will simply write out the first line here. First will be our matrix, the first register times parentheses are okay, this is okay, and we will multiply that by all the diagonals, it seems. All the diagonals here times each other. Minus let's see, let's do the semicolon so I don't have to bother doing this all the time. minus, no, plus actually, plus times plus and then plus some more stuff here. Yeah, usually I do, but yeah, that's a good suggestion. Thank you very much. Usually I use the AVX intrinsics, but for this I haven't looked up the way to do it in terms of intrinsics, so I'll be doing it manually. It's quite verbose, so it takes a bit of time here. So 1 and 3 times 2 times, whoops, this needs to be times, of course, and we do, wait a minute. Yeah, I looked up the wrong place here. So 1, 4, 2, 1 here, and 3, 2. Yeah. There are probably a lot of ways that would be easier. So let's see. This is correct. 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 And then we start with the negatives here. Which will be 1, 4 times 2, 2 times 3, 1 and minus 1, 2 times 2, 1 times 3, 3. And then the last one here. Oh, I got distracted. This is rather boring. Yeah, I should really use, let's see. Well, did I mess this up? I might have. No, I didn't. Two, three, and well, okay. So that's the first line. Then we will do the second line. Let me just copy this and edit it because I think it follows the same pattern. Yeah, yeah. Second. Whoops. Okay, let's see. So we do this one, and then this is supposed to be 0, 1. This is supposed to be like that. This is supposed to be like that, so that's fine. This is supposed to be 0 here. And this is supposed to be like that. And this is supposed to be, whoops. And this is supposed to be like that. Okay. Then we will have this changed into a 0. This is fine. This is fine. Okay. This will be 0. The next one is fine. The last one is fine. We will change this. And I probably should change the last one as well. Yeah. Yeah, so that changes like that. Then we have the third term here. Oh, whoops. Well, yeah. Then we will change this term here. And the rest is the same. Next line. We will change this one. And the next line here, of course, we change this one. And down here, we change this one. Down here, of course, well, the pattern is pretty obvious now. And then the last term. Okay, let's see. We change this to that. And then the last term here changes. And I'm supposing that everything works exactly the same. It does seem like it. Okay, so the determinant is equal to first minus second plus third minus fourth. Great stuff. That's the determinant at last. Let's do a temporary debugging here. Good luck, buddy. Good luck, buddy. So we will load determinant. Yeah, fingers crossed. Matrix inverse 4x4. And let's get our MP app here, camera controller, camera, get view matrix. Let's print out the determinant. Let's enter editor mode, and determinant is 1. At least it thinks so. Let's see. Anyway, okay. Let's see, let's try printing the register here. I think the matrix here, yeah, it prints out in row major version. Let's see if we pass it this view matrix, and we pass it that, we will get our view matrix here. Let's see if we take a online calculator somewhere. Calculator, determinant, matrix. Let's do a test here. We enter 1, 0. And we pass in that minus 14 and then 1. Well, the determinant is 1. So our calculator seems to be correct, which is great, at least from this singular test. Meaning that we can actually disable this. revert back to a G matrix here. And return the result. Okay, so next we will do the, what do you call it, adjoint. Let's see. I really want to get this done. Cofactor, or rather, adjoint matrix 4x4. Oh man. Okay. Okay. Yeah, so we have the determinant. We need the, yeah, we've done that. Okay. So we will actually use a submatrix. Okay. So we actually don't need the determinant for the whole 4 by 4 matrix. Let's see, is that what we actually do here? I actually think it is. It's the 3 by 3 determinants. It seems, at least, let's see. Yeah. Yeah. So without this, we actually have our submatrix determinants. Let's see. Okay, okay, okay. I think I got this. I think I got this. So I think we need to, we have the 3x3 determinants here. And we can easily calculate the actual the determinant here is equal to the matrix register 0 here times the first minus the matrix register here plus matrix D second first register, whoops, times that, and then matrix D3 first register, I think, yeah, times this. So this is the determinant of the matrix. I don't know about OpenGL, but generally UV mapping is mapped between those coordinates. I think OpenGL UV mapping is different than um, DirectX in terms of the direction of the axis, but I'm not sure. Okay, so we have a determinant. R2244. Okay, we need further, we need some additional determinants here. Oh man, do I really have to calculate all of those? It seems like it. Oh yeah. Let's do float A11 And we will yeah. Okay, let's paste this. Every texture is mapped into that coordinate space. So the outer edge of any texture is one either on the x or y axis. Okay, let's see. I'm gonna use your suggestion. SymPy, Cogen, matrix inverse, 4 times 4. I think I'm getting impatient now. I don't have. Oh my god. I'm getting so impatient here. Anyway. Anyway. Let me just do this quickly. No distractions. So 1, 1, 2, 2, 3, 3. Then 3, 1. 3, 2, 2, 1. 1, 3. 2, 1. 3, 2. And then 1, 4. 3, 3. 3, 1. 1, 2. 2, 1, 3, 3. 1, 1. Oh, whoops. 2, 3, and 3, 2. Okay. This stuff is computatively expensive. Okay, the signs are flipped here, so minus, minus, plus, plus, plus. So this should change. Whoops. Let's see. This changes. Yeah, so this should also just decrease here. Whoops, no. So this changes. This changes. This changes. Yeah, it's fine. I'll probably be done with this shortly, but yeah, I'll look into a better method off stream. I use this part of my math knowledge so seldomly that okay, we change the next one. And it seems like we do it. Yeah, so this is basically just this instead, I think, if I'm not mistaken. Yeah, and we flip the signs, right? So, whoops. So that is plus plus. Okay. Let's create the next one here. Which will have a negative sign here. This will be subtracted, plus, plus, plus. And then the last component here will change, decrementing this. There we go. Thank you. I'll look into it in a short while. I'll just fix this up. Let's see, minus, minus. Well, we start out with that. Then we need a a 1 0 here, a 2 2 here, a 3 3 here, and then a 1 2 here, 2 3 here, 3 0 here, 1 3, 2 1, Or rather 2 0. And then 3 2 1 3 3 2 2 rather. 3 0 here. And then 1 2 and then 3 3 and the last component here 1 0 2 3 and then 3 2. Okay, great stuff. And I suspect that this will be fairly quickly to change. Let's just change all these signs here. Since it will probably look a lot like, yeah, so we simply reduce this. I'm pretty sure. Yeah. So that's that. Let's see the next one here. We're getting close. We're getting close. And we reduce this by 1. Great stuff. And the last one of this row here. Man, this is cumbersome. Let's see. And the last one changes by reducing by 1, I think. Yeah. That's it. Okay. That's halfway to go of this fellow here. All right, let's do let's do 1 0 here, 2 1 and 3 3. 1 1 2 3 3 0. 1 3 2 0 and then 3 1. Is that correct? Yeah, it is. Okay. Then we do 1 3 2 1 3 0. Then we do 1 1 2 0 3 3. And then this one 1 0 2 3 and then 3 1. Must be Einstein. No, 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 no. Definitely no Einstein here. Uh, I'm copying someone else's formula. This is a part of linear algebra that I'm not very good at. So I have to kind of use what other people have made. Of formulas. Okay. We reduce the first component here, it seems. Yeah, that's basically what we do. So we reduce this. And we flip the signs. Okay. I flip the sign. Plus, plus. But it will be great to be done with this. Okay, it's our third time, and then this needs to be reduced by 1. And then our fourth time here. Whoops. Will be negated, and then yeah, you are most likely right, sir. Well, the formula I haven't written myself. This guy has created a cofactor calculation. I mean, it's fairly expensive to do like this. We should find some optimized way of doing it. It's fairly expensive. Anyway, we're soon to be done here, which is awesome because I will soon need to go. So I'd like for us to arrive at a state where we can actually create a ray in object space and cast that. Let's see. When we click on the screen, I want to be able to cast a ray that displays where we would look for objects when we click. Let's see, 3, 2. That's it. Then this one, 1, 1, 2, 2, and then 4, 0. Then the 1, 2 here, 2, 0, and then 3, 1. Is it open source and non-copyrighted, or the MKL? Because for this computation here, I think I'll use what's ever available. It seems cumbersome to do. Yeah, I'm gonna go at least in not too much in too long time. I can't speak right now. Let's see. So this one has 2, 3. Yeah, so I got done with this. So let's see. 1, 2, 2, 1, 3, 0, and then 1, 1, 2, 0. 3, 2, and then the last one, and then we will start getting into the easy part. Oh, great, man! I'll use whatever algorithm they have developed. Okay, we decrease the first component here. And we create the next one here. Oh, that's 2, 3, of course. This is going to be negative, minus, minus, plus, plus, plus. And in this version, we decrease the second component here. And then the last component. Yeah, and as usual, we decrease the last column specifier. Okay. And we only need to okay. So we can start filling our result here. Let's see. So the first component here will be divided by our determinant. Okay. Let's see, we do it in column order. So, whoops. Okay, everything compiles even though we didn't need to. There we go. And let's do the same for the next column here. Let's do 2, 2, 2, 2. And the last column. Whoops, this is supposed to be 4, of course. There we go. Okay. Let's compare the results just to be certain that our calculations are correct. Print matrix. Come on, buddy. Inverse. And original. Let's just debug that. Slash test it. Let's see. So we enter editor mode and let's see if we inverse matrix calculator. Let's do 1, 1, 1, 1 minus 14, and then this. Well, our result is correct, at least for this version. So, isn't that great? Our implementation works. So, we would like to translate our vector here, redirection, into object space, or rather world space coordinates. Math. Thank you very much. It took some time. Let's see. Back. Vector multiplier matrix. Let's put in our array direction and then get our inverse view matrix here. And let's print out our array in world space coordinates. Okay. Let's see. Let's enter the editor mode and then, okay. So if we click here, we're moving in a slightly negative angle on the x-axis. Let's see, is this correct? Is this actually correct? Okay, if I change the camera here and move out like this, let's see if I change this. Oh, well, oh, that's fine. Let's do. No, that should be all right. Let's see. Okay. If our calculations are correct, we have we of course also need the origin to be. Maybe we want to store the matrix instead of inverse view matrix, instead of computing it twice. That seems like a good way to do things. Let's translate the origin as well. Array origin here and our inverse view matrix. And let's print out our origin and our direction. And let's see how where that gets us. Well, maybe we want to normalize this as well. Just vector normalize vec3 normalize. There we go. Our array origin is along the positive, or rather, yeah, so it's pointing a bit down. That definitely makes sense. So if we move our camera here into the origin of world space, our origin moves particularly close to the actual position in world space. So that's great. You can see our Y position on the origin is pretty high up, which corresponds to the camera. The C and the X components are close to 0. So when I click here, the ray gets cast from the camera, and it points, well, yeah, we should just cast some rays inside our world, since we will be able to do that. The problem is that we want to transfer this to our renderer. Uh, let's see. Let's see. So is it never negative? Let's see if we point upwards in terms of our y-axis here. Well, the y component never seems to be negative for some reason. I find that somewhat peculiar. Now it is. Although it's not very negative. Okay, this time it's very negative. I'm pretty sure this is because we rotate the camera. Okay. Well, I'd have to debug this a bit. I mean, does the ray actually seem correct? The ray origin does seem correct. At least as long as I haven't rotated the actual camera. I'm unsure when I rotate whether I get the correct inverse matrix. Maybe I actually need to transpose it because Yeah, I think it might be transposed here. I can always just flip it inside the function, transpose it there. Anyway, let's see. Well, this does seem more like it. Yeah, I think I have to transpose it because the result is well, is it not? Well, let's see. This does seem more correct at least because, well, not the origin at least. The origin doesn't make any sense. But the direction is probable. Yeah, the origin is not correct. Huh. Yeah, so if I don't transpose, I end up in a situation where the origin is not correct, but the direction vector does seem a bit funky, doesn't it? I mean, I guess that's correct. It's supposed to point downwards on the z-axis. Let's see. Did we change? Let's see. Let's move to this camera here. Because I might not have changed the camera. Well, yeah. The origin does seem... No, because it's rotated. Get camera. We update our camera. Inside our camera function here. Update view matrix. That should get updated inside our camera controller, I think. Let's see. Update view matrix. I guess there's no other option than actually casting the ray, drawing it. Ray direction very high on the X. Yeah. We will do something kind of hacky here. Kind of hacky. So our debug system here allows us to submit some lines. If we're in debug mode, we can actually print the lines. We could create a internal buffer that has some lines. We would need a debug primitive to be passed along to our application here. Okay, we will do that. We will do a hacky thing here. Hacky should not be kept. Let's do a private temporary stuff. Let's do a vector of debug primitives m lines race void cast ray debug. Where we will take a g float, no, a g vector reference origin g vector reference direction. We will do this right here. So we will compute our debug primitive stuff. So for a line, the sender, then we simply set the endpoint and then the color. So we will create a debug primitive, temp primitive, where we will call math load float 3, store float 3, temp primitive here, position, and we will store the origin. We will pass that by reference here. And let's see, g vector endpoint will be our math scalar vector multiply scalar direction times maybe 50. And we want to math store float 3 on the temp prim position 2. And we want to store our endpoint here. And we will set our temp prim color to be equal to something that is yellowish. Let's do some yellow here. I think that's yellow, right? Green and blue. Let's see. Store field 4. Okay, and we add that to our arrays here. Yeah, add our temp prim here. Okay, so inside our level system here, we can actually ask our papp here, mpapp, cast ray debug, ray origin, whoops, and ray direction. And then we simply insert debug lines.end, and we mraise begin, mraise end lines. We simply insert that. So this should create some debug lines. Let's just enable debug mode. Let's cast a ray. Okay. We get 2 rays, even though they are pretty weird. Okay. These rays are definitely not correct, I'd reckon. Okay. mm. Let's see. Why does it create 2 anyway? Oh, maybe because I click whenever I toggle the debug info. Okay, let's bind. Let's bind. Set debug mode. Let's do mdebug mode 2. And we set debug mode here. Mdebug mode is equal to the opposite of debug mode. So now we can toggle that with the F keys here. Great stuff. Okay. Let's enter editor mode and let's set debug mode and let's cast array. Well, I feel like it's kind of like the opposite of what I've expected. So we cast that ray and it goes in the completely opposite direction. Let's see. So if I cast array here, well, for some reason it flies off to the side. Okay. There might be a problem with our inverted matrix here. There might be a problem with our computation of our x and y coordinates. Let me just double check that everything is as it's supposed to be. The keyword should be supposed to be, oh, maybe we don't want the translation here on the direction, but we do want it on the origin. Yeah, the direction shouldn't be offset in any kind of way. Okay, let's enter editor mode. Editor mode. Well, it still doesn't exactly work as I thought it would. Let's see. Let me just turn around the camera. Yeah, okay. So nothing happens. Let's just print out whenever we castrate. Uh, yeah. Also, I need to make sure that the formula that I'm using is not based on a right-hand sided coordinate system, or rather left-hand sided, I think. I need to work through this cast array. Whoops, we need to enable debug mode. So yeah, I think, okay, let's try swapping the camera here and casting array. Well, it goes parallel to that. That doesn't make any sense. I mean, this doesn't make any sense. The rays are really, really weird. Okay, I have to debug that. Okay, let's see. Let's print the X and Y. um, Y. Oh, I also have to go soon, so I probably won't be able to do it today. So whenever I click here, I get a x coordinate close to 0, but up here, well, that is close to 1, 1. I'm not sure that is how I want it. Is it? Let's see. No, I think the y is inverted here. Yeah, but I'm not translating from local to global. I'm translating from view space back into world space. I'm translating all the way from normalized device coordinates into world space. But I think our mapping here of the y component is incorrect. Let's try swapping this. Weren't you talking about from object space into world space? Or maybe I misunderstood you. Anyway, let's do this instead. Let's do 1. Oh, okay. Well, yeah. Hi, MC Key. You are right in that regard. That's the math behind it, but yeah. In general, my transformations between different coordinates and bases work fine. I think the problem is the normalized device coordinates that I feed to the algorithm. Let's see. So times 2 minus 1 here. Let's try doing that instead. Or maybe the projection matrix is actually doing that for us. Let's see. Yeah, it might be. Yeah, I think it might be. Okay. MX, MY will be our mouse pos. The X mouse pos the Y here. Just to be certain that everything is all right. Let's see. Whoops. Huh. Let's see. Let's see. Projection matrix. Left hand side. DirectX. Let's see. If we Uh, and if we, there we go, let's step into this one. Projection. Look to left-handed. View and projection. Look, that's not it. Blah blah blah. Perspective left. So maybe we need to flip that because if it's for a left-handed coordinate system projection. Let's see, let's do another one. Perspective, right hand, view width, height, field of view, height divided by the aspect ratio. Well, it should be the same. Yeah. Let's see, maybe width is divided by the height divided by the aspect ratio. Let's see if perspective FOV right-handed, is that the, yeah, that's the exact same one. The width is calculated in the same way. The height cosinus FOV to the sine of FOV. Yeah, it's exactly the same. So that component we divide with, let's see, let's remove that. So it's not that division that is the problem. That should be fine. So close to our screen center here. Yeah. And the X out here. Well, that does seem reasonable that the X values are the one that changes. Oh, I really hit the Y almost at the 0 here. So that's the middle of the screen, and this is the middle of the screen, and this is probably around the middle of the screen. And then this down here is the opposite. I'm not sure it gets scaled correctly. I'm not sure. I mean, this diagonal here shouldn't change. Um, I don't think the Win32 API can, but I'm not sure. You can deduct it, I guess. Oh, I really need to go, man. I don't have time anymore. Anyway, I'll have to debug this some other day. Uh, yeah, I gotta go. I wanted to spend a few hours here and ended up spending almost 4 hours. Um, anyway, whoops. Let's see. In our debug mode here, we kind of like cast the maybe if we negate it, just let me try negating the. Yeah, yeah. Good luck on your test, man. I hope you ace it just as you want. Vector. Let's see. It doesn't look right, but it does look better. Well, it just shoots directly for the origin in, or maybe it just shoots from the origin. Okay. Never mind. We will bother with that some other day. Okay. Thanks for everyone who dropped by and interacted during the stream. Hopefully I'll get this fixed. I will eventually, but yeah, it probably takes some debugging. Um, if you're watching this in the future, feel free to comment, like, or subscribe if you found it helpful, inspirational, or just even a tad entertaining. Be sure to into on check out the stream whenever I'm here. We have a nice community, little community going. Um, Lots of tech interested dudes, and we also seem to have gotten a pretty math knowledgeable dude in here, so that was great. Anyway, everyone take care, stay healthy, take care of yourselves, and hopefully I'll see you around. Bye bye.